always nice to have that confirmation. Okay, so actually I'm going to flip my headphones around, sorry. Kind of throws me off when the mic's on the other side. All right, we're talking about, sorry, I don't know why it says feature selection here. We're talking about this, about decision trees. So decision trees are my personal pet favorite model. Oh, actually, sorry, I don't know why I flipped back. So a lot of people like to use logistic regression as their sort of staple default first pass model. I actually, I fall differently on this equation. I actually move towards decision trees for reasons we can discuss if anybody has questions. But one way or another, it is one of those models you just have to know. And it's one of those models that relatively few people understand deeply enough to explain how it works bottom up. And so what I want to do today is walk everybody through decision trees from scratch so that we all have an understanding of really how these things work from at a really fundamental level. And yeah, and we'll see where that takes us. But feel free to interrupt at any point along the way if you have questions. For starters, I just want to motivate this a little bit, provide a little bit of a teaser. Part of the reason why I like decision trees over alternatives is interpretability. So first and foremost, decision trees are, as we'll get into here, a game of 20 questions that you play with your data set. Right? So you have a bunch of yes or no questions that you're able to ask at each level of the tree to split your data up. So you have a whole training data set, and you're basically splitting that data set up into sub-data sets. And you do that by asking some very well-defined questions. And so in this case, well, I'm Canadian, so we'll be talking about a hockey example here. We're going to imagine we have a whole bunch of different hockey players, and those players have different attributes. For example, height, weight, the amount of time they spend on average on the ice during a game, which is this average ice time thing, and so on. So there are all these very well-characterized, well-understood variables, and we're asking a single well-defined question about one of those variables every time we split that data set. Right? So for example here, the very first question we're asking is the height of the player less than 6'1", or I should say 6.1 feet, right? If the answer is yes, that sample is going to fall into the true bucket. If the answer is no, it falls into the false bucket. And so we have this division of our training set into two different kind of groups of samples, two different sub-data sets, if you will. That's a really easy thing to understand, right? It's this concrete variable. I know what it means for the height to be less than or equal to 6 feet. So that's one of the advantages here as well. So you can really follow the logic of a decision tree very, very closely and audit it carefully. There are a whole bunch of other, I'll say, surprising features of decision trees that make them surprisingly robust, surprisingly kind of adaptive to different types of correlations in your data. And we will get into that. But again, I want to go bottom up here and give you a sense for how these things work to begin with. First of all, just from that general picture, like when I say decision trees are a game of 20 questions, I assume most people are basically familiar with that concept. But does anybody have any general questions about like what decision trees are before I dive into how they work and sort of the hand-wavy math behind them? It's okay if not, but okay. All right, cool. I'll assume not. So let's get started with laying out like a really, really concrete example. Okay, so we're going to imagine we have a training set. This training set contains a whole bunch of hockey players. How many hockey players? 512. And so we have this data set, this training data set of 512 hockey players. They have a series of features. So we'll imagine they have maybe 10 different features, 10 different attributes. And these are things like player height, player weight, the average ice time that the player spends on the ice during a game, the salary of the player, and so on. So 10 different columns in this data set and 512 rows. Okay. So what we're going to do is we're going to imagine putting those 512 samples into a bucket of data, and that's represented by this first sort of rounded rectangle at the very top here. Okay, so this bucket at the very top represents our entire data set, the whole training data set. And I'm really going to emphasize the training data set. We're not talking about validation. We're not talking about testing or runtime. This is strictly the training process that we're about to look at. And you'll see once you understand the training process, the sort of, what do you call it, the inference time process is trivially, you can extrapolate trivially to understand how that works. So 512 players, and that's what this samples thing means here. Samples equals 512. I'll just zoom in a little bit so you can see that more. So 512 players. We also have another number here. Now, the goal of this process is going to be to build a decision tree that can predict something. And what are we trying to predict? Well, we're trying to predict, in this particular example, the number of goals that a player is going to score over the course of a hockey season. Okay, so we have 10 features, and then the 11th column is actually going to be the number of goals scored during the hockey season we're interested in. And what this value thing is here is it's the average value of the thing we're trying to predict, the thing we're interested in predicting. Okay, so the average, in this case, number of goals scored over the course of a season across this whole training data set. So we have these 512 players, and on average, those players are scoring 21.4 goals in a season. Okay, so value is always going to, like, you can print out this, this sort of decision tree map in scikit-learn. And when you do, you're actually going to see these things. You're going to see height, MSE, samples, and value. Value is always going to represent the average of the thing you're trying to predict, the thing you're doing regression on. In this case, we're doing decision trees for regression. So 512 samples, on average they're scoring, or 512 players I should say, on average those players scoring 21.4 goals, good. There is then this very last number here, MSE. Okay, so MSE is the mean squared error. So let's take a step back and sort of think about mean squared error for a second, right? The mean squared error is the number that tells you how wrong on average your model was when you're doing regression. So say you have some kind of regression model, right? A model that can predict, well, let's say in this case, like the number of goals scored by a given hockey player in a given season. You try to make those predictions across a whole, I don't know, testing set or training set or whatever, a whole data set. And on average, you're going to be wrong by a certain mean squared error. The mean squared error is a measure of how wrong you are on average across the data set that you're trying to run your predictions on. So one thing that might seem curious is, like, how do we have a mean squared error here when we don't even have a model? Like, we have this data set. It's got 512 hockey players. On average, we have, sure, the number of goals that those players score, but how come we already have a mean squared error? Like, what is the prediction that this mean squared error is referring to? And this is where we get into a little bit of machine learning philosophy. Okay, so machine learning can be much simpler than most people think. There are algorithms, in fact, that are so simple that most of us don't even think of them as machine learning algorithms, and one of them is the statistical average. When you take the average of a sample of data, so let's say you're trying to predict the number of people, the number of people who are going to go vote for Joe Biden or Donald Trump or whatever, the average is actually a model. The more samples you collect, the more accurate your prediction is going to be for the average number of people who vote for a given candidate. Yeah, I mean, it just like a machine learning model, you throw more data at it, and the accuracy of the model tends to go up. It makes certain assumptions about, you know, unipolarity of the distribution or whatever, but that's fine. It's still basically a machine learning model. You feed in data, and then you make a prediction. It's just that it happens to use just one feature, and it just takes the average of that feature to spit out the prediction of the model, but the average is still a machine learning model. So why am I talking about averages as machine learning models? Well, that's because that's exactly how decision trees are going to work. So we have this bucket that contains all 512 of our players. On average, those players are scoring 21.4 goals. And if that was the only piece of information you had about those players, and I asked you to make a prediction, I pick one of those 512 players at random, and I ask you, hey, make a prediction about how many goals you think this player is going to score, on average, you would guess the average. That's the best way to predict the number of goals that player will score. And when you do that, you will be wrong by a mean squared error, in this case, of 11.09. Okay, so this mean squared error is telling you how bad, basically how bad this average value is as a predictor for the number of goals scored by every individual sample in this data set. Okay? So if that MSE is really high, then that means, hey, if you just use this average number of goals scored, you're not going to be very accurate. Like, you should expect it to be off by a lot if you just pick out one of those 512 players at random. So in other words, it means there's a big spread, right? There's a big spread of goals, so you shouldn't expect any given player out of that set of 512 to be particularly close to the average. They're all kind of spread out. Does that make sense to everybody? Does anybody have questions about that? Cheyenne, you good? Oh, Nicola, yeah,
So
go
just
ahead.
to confirm, basically the first thing that happens is it takes an average, and then we take the mean squared error off of that average, and we just use average as a prediction, basically. That's how it calculates mean squared average.
Correct. Yeah, and there's a formula like for mean squared
Okay.
error where
Yeah.
yeah,
That makes sense.
yeah, exactly. So I mean, you can almost think of it as like the standard deviation or the variance of this data set,
Yeah,
right?
that's kind of what it
Or
is.
of the thing.
That makes sense. Yeah, and I always keep forgetting that whenever I go through one of these decision tree office hours, I always forget that before that I always get surprised that you think of an average as a prediction, but it makes so much sense. It's pretty cool.
Yeah, yeah. There are a lot of sort of funny things like that in the philosophy of machine learning, like what counts as machine learning and what doesn't. But you're absolutely right. It's one of those counterintuitive things. Yeah. So actually, yeah, to Nicola's point, I mean, really, this MSE, it's like the standard deviation. It's like the variance of your thing that you're trying to predict. Again, in this case, the number of goals scored by these players over the course of a season. So, to summarize, I know it sounds like I'm beating a dead horse here, but I think like if you can really land this and kind of get this first part concrete, everything else is going to be that much simpler. So we've got 512 hockey players, right? Those players have 10, let's say 10 different features. And we're trying to predict the number of goals that those players are going to score in a given season. On average, these 512 players, so all the players in this bucket at the very top, they're going to score on average 21.4 goals in a season. Now, how good is that average as a predictor for the number of goals scored by any given player in the data set? Well, it's going to be off by a mean squared error on average of 11.09. So that's how to read this, basically. Okay. Now, at the very top here, there's a threshold that says if the height of the player is less than or equal to 6.1, then move the player over into this bucket. And if not, move the player over into this bucket, which immediately invites the question, how did we come up with that threshold and why is it being used to split the data in this way? So how did the algorithm know which question to ask? And that's a really good question that I'm going to defer. I'm going to defer it to the next step in this process. I'm going to explain a little bit more stuff, and then we'll retroactively explain how it is that we came up with this threshold. For now, let's just imagine that we were handed this threshold from on high. Some oracle came in and said, hey, the very best possible question that you can ask is the height less than or equal to 6.1? And we'll explain how exactly that oracle came to that conclusion in just a second. But first, we have to go back or go sort of forward to this next layer of the tree. So if the hockey player, has a height that's less than 6.1 feet, he ends up in this bucket. If not, he ends up in this bucket. Okay, first thing we got to do is we got to check our math to see if this makes sense. You'll notice these buckets have all of the same variables in them. They all have MSE, samples, and value. You'll notice, so samples again, that's the number of players who end up in that bucket after the split from the previous level, right? So we had 512 samples here initially, 512 hockey players. 272 of them end up in the left bucket, and 240 end up in the right bucket, and 272 plus 240 does equal to 512. So that should kind of be a basic sanity check. Okay, everything kind of makes sense at a basic level here. Okay, now let's look at the value. So value, again, this is the average number of goals scored by the players who made it into this bucket. So we have 272 players who are indeed shorter than 6.1 feet. And the average number of goals scored by those 272 players is 24.1. So on average, those players are scoring 24.1 goals in a season. If we go to the other bucket, we have 240 players, and on average, they're scoring 17.3 goals. So it actually seems like height is inversely correlated to number of goals scored, at least at this level of the tree. So if you're shorter than 6.1 feet, you're scoring more goals on average than if you're not. So maybe that's not realistic. I don't know, but let's just go with it. So that's the basic idea. We know how to read these two buckets, and let's check out that MSE. So on average, what this is saying is if you took one of these 272 players and you guessed, I don't know how many goals this guy's going to score, but let me just assume that it's the average, right? So let me just assume that it's 24.1 goals. You would be wrong if you did that by a mean squared error of 3.43 goals on average, right? And over here, if you looked at these 240 players and you guessed that a given one of those players was going to score 17.3 goals, you'd be wrong by an average of an MSE of 4.56. Okay. One thing you might notice is that the MSEs have dropped, right? 3.43 and 4.56 are definitely smaller than 11.09. So what that means is the average is now a better guess for the true number of goals scored by a given player in each of these buckets. So that kind of seems interesting, right? It sort of seems like this tree has split up our samples in a way that is somehow good, or at least in a way that makes the average a better predictor. And the question is, how do we figure out how to make that determination? How do we figure out how to split the data set in just that way? Okay. Well, these two numbers, the MSE of 3.43 and the MSE of 4.56, those do provide us then with a kind of measure for how good the question was that we asked to get here, right? Like if we asked a really amazing question and it just split our data up in a perfect way so that like every player in this bucket scored exactly 24 goals and every player in this bucket scored exactly 17 goals, then our MSEs would actually be 0 because the mean would be exactly the same as the true value for each of the samples in those buckets, right? So there's a sense in which the lower the MSE is in these two buckets, the better. The better of a job we've done in asking this question up here, which kind of suggests a strategy. Maybe we can use these MSEs as a way of deciding what question to ask. In other words, maybe we can just work backwards. And that's in fact exactly what the decision tree algorithm is going to do, with one little caveat. And that is that currently we have two MSEs, right? Two different values. How can we use two different values to make one decision about which question to ask? And the answer is, I mean, you can't. You need a single number that you can use to measure the goodness of a particular question. And so we're going to have to find a way to combine these two MSEs together into one number that tells us how good or bad a given question is. Does anybody have any ideas how we might do that? So again, we have an MSE in one bucket that tells you like how pure basically this bucket is, or how good the average number of goals scored for players in this bucket is as a prediction for the true number of goals scored by each player in this bucket. And then we have another MSE that does the same thing for the other bucket. How can we combine those two MSEs to give a single number that's going to help us decide how good a question is?
I was going to say purity, but you kind of gave a hint already. We want to increase purity and reduce impurity. I'm putting air quotes, but I can't remember a math equation on top of my head, but that's basically it.
Okay, so you're right in terms of the almost the emotion of it. Yeah, we want to measure purity, but I guess the question is, how do we get a single number for purity out of these two numbers, right? We have an MSE for the first bucket and an MSE for the second bucket, but we kind of need like one single number that we can point to and say, oh, like the MSE for this question, like for height less than 6.1 is really, really low, but the MSE for height less than 5 is a little bit higher, so let's stick with 6.1, right? So we want a single number that combines these two together. Does anybody have any thoughts about how to do that? I'll pick on Chris, yeah, go ahead.
Sorry, what if this won't necessarily make it like better at each one, but if you take the absolute difference, then at least you know you're picking like a split that will not like overly favor one bucket or the other. I'm not sure if that's like a good way to do it, but that's just a random idea.
Okay, this is promising. Yeah, you flagged something that matters. Can you elaborate on what you mean by absolute difference?
Because basically I was thinking like one of the traps you could fall into is if that you picked like a feature that, like, I don't know, say in a really trivial case, you picked like, oh, if the name of the player is equal to like John, then it'll split the data set into like a bucket of like one player, and it'll have like a perfect prediction for one player, and then it'll just lump everyone else in. And like the model might think that's good because the mean squared error of that one bucket would be effectively 0.
Awesome.
So you want to consider like between the two, I think. Like you don't want to let one bucket's mean squared error be like too much bigger than the others. But I don't know how to actually reduce it to pick like the lowest one. I'm sure there's like a math formula that I'm trying to think of now, but yeah.
So you just latched on to actually the trick part of the question that I was going to toss in at the end. That's the hard part of this.
Okay.
So I hope, just to check in, like, is everybody clear on what Chris said there? Does anybody have any questions, or did anybody have any trouble following that reasoning? Okay, cool. So I'll give you the answer. And so I'll give you the answer starting with the stupid answer that I first would have given to this, which would have been to say, look, we have two different numbers, right? We have the first mean squared error for the first bucket and the second mean squared error for the second one. Well, why don't we just take the average, right? Why don't we just take the average mean squared error, and then we'll say, great, we have one number that we can optimize. But then Chris comes in and says, well, wait a minute. What if you have a perverse setup like you just flagged, where you end up, maybe there's one player who's like shorter than 5'2" or something, and so if you picked height less than 5'2", you would have a single sample in one of the buckets, and because there's a single sample in that bucket, the average number of goals scored by all the samples in that bucket will be exactly the same as the true number of goals scored by all the samples in that bucket. So the MSE will actually be 0. There's no error. Like, the true and average values converge because there's just n equals 1. And so that would cause the MSE here to be 0, and then the other MSE to be, I don't know, probably close to whatever the original one was. And then on average, that could actually give you a really good score, even though the question was just kind of perversely messed up. And so the question is, how do you deal with that possibility? And the answer is you do a weighted average. So you notice how we have the number of samples in each bucket? The logic here is going to be to say, okay, in this bucket, I have a mean squared error of 3.43. So 3.43 is a measure of like how bad this average is as a measure for the true value of each of these 722 samples, right? So how close to 24.1 is the true number of goals scored on average of these 272 players? Well, it's off on average by an MSE of 3.43. So if 3.43, we have an MSE of 3.43 that applies to these 272 players. We have an MSE of 4.56 that applies to these 240 players. So if we do a weighted average, if we weight these MSEs by the number of samples in their respective buckets, then that's going to give us a nicely balanced measure of the kind of average MSE, if you will, the thing that we care about. This deals with Chris's scenario, because if we had a perverse split where we had just like one sample that showed up in this bucket, then it would make a tiny contribution to the overall MSE. So like, sure, the MSE would be 0 here, but you'd only have one sample, and like all 511 other samples would be way over here, and so pretty much whatever the MSE of that bucket was, it would determine roughly what the overall MSE was. So yeah, the key here is to do a weighted average. I hope that makes sense. Does anybody, like Chris, does that make sense, given that you're the one who flagged this?
Yeah, no, that's an awesome way. Good explanation.
Perfect.
Thanks.
Yeah, no problem. And just to check in, I'm going to pick on one or two people to make sure everything's cool, but Hadrian, is everything good?
Yeah, it's a great explanation. I just want to, I was just looking through my notes, and I recall writing something akin to, for every split, the objective is to gain as much information from it for every split. And I'm just wondering, how is that quantified?
Good. Yes.
If I'm not, if I'm not wrong in my my reasoning.
No, your reasoning is correct. The word so I guess the question is, what does the word information mean, right, in this context? And in this context, information refers to the purity, basically, of these buckets. So very, very pure buckets. The way you could say this in colloquial language is, if I'm in a bucket with a very, very low MSE, then the average value of the samples in that bucket tells me a lot of information about the true value of each individual sample in this bucket. So to make this even more concrete, let's say that we have a bunch of hockey players who get into a club, and it's called like the 25 goal scorers club. Okay, and this is just for players who scored exactly 25 goals in a season, right? So in this case, if you had that feature, oh, this guy's in the 25 goal scorers club, right? That feature would carry a lot of information about the thing you care about, the number of goals scored. So if you ended up using that as a splitting point, for various reasons that actually might not be a great feature to use, but it doesn't matter. Just for illustrative purposes, the point is that just a sample being in that bucket would give you a lot of information about what the number of goals scored by that player is. So in this case, if the MSE is really low, that means that the average here gives you a lot of information about individual cases. So it's a very pure bucket. The average is very close to the true value for all these samples. It doesn't have a wide distribution. If it had a really wide distribution, there wouldn't be much information about an individual sample. Like if you knew that a player was in this bucket, that wouldn't really tell you much about like how likely that player was to score a particular number of goals. Sorry, I think I might have mangled that explanation, but I hope that made some sense.
No, that's clear.
Okay. Okay, great. So we now have our game plan. We have a way of coming up with a single number that tells us how good or bad a particular question is. So specifically, if I give you a question like, is the height of a player less than or equal to 6.1, you now can go, okay, well, I'll tell you what. I'll take that split point, I'll split my samples up, I'll put the players for whom the answer to that question is true into one bucket, and I'll put the other players into another bucket. I will calculate the mean squared error I will calculate the average number of goals scored by players in that bucket, and I'll see how wrong that is on average, what the mean squared error of that prediction is for that bucket in each case, and then I'll take the weighted average mean squared error of these buckets, and that's going to give me a single number that tells me how good that original question was. Okay. This might sound really actually kind of stupid in a way, because it implies that what decision trees are doing is actually brute force trial and error. And amazingly, that's exactly how decision trees are built. So what you do in a decision tree is, in this case, we have 512 hockey players. We said we had 10 different columns, so 10 different features. And what you're going to do is you pick a column, like height, for example. You sort your players from shortest to tallest. You test out every possible way of splitting up the players based on that column. So you say, okay, I'll take the shortest player, I'll move him over into this bucket, and I'll take all 511 of the tallest players, I'll move them into this bucket. I'll calculate the weighted average mean squared error for that particular split, and I'll store that number. And then try again. Okay, I'll take the shortest 2 players, move them into this bucket. I'll take all 510 tallest players, put them in the other bucket, repeat. Then shortest 3 players, then shortest 4 players, and so on. Every possible way of splitting that column. And you're going to then do that for all the columns. So you're going to try, it ends up being 511 different ways of splitting up a single column. And then you have 10 columns, so it's 10 times 511, so like over 5,000 different trial and error runs that you're going to have to do for your 512 hockey players in order to figure out which is the one that minimizes the weighted average mean squared error of the next layer in the decision tree. And once you found it, boom, that becomes the question that you ask. Does that make sense?
It does. I just have a follow-up question, I guess, for the weights are determined by the sample size. So the bigger the sample size, the more weight a bucket has, quote unquote.
Yeah, that's one way to look at it. That's right, because we're doing, weighted average mean squared error. So like I should have given a formula, but basically it's going to be 272 times 3.43.
Yeah, that makes sense, yeah.
Plus 240, times 4.56 divided by 512 to normalize.
Yeah. Thank you.
Yeah, no problem.
Yeah, I just had a quick question. Like, so in that kind of brute forcing process where you're basically testing every split, do you do that across every feature as well?
Correct.
Okay.
Yeah. And so this is really where I think our intuitions often fail us. Like when I first learned this, I was kind of dismayed and disappointed, right? Because it's kind of a dumb strategy. Like it doesn't feel like the kind of smart that I usually associate with machine learning. But the short answer is it's made possible because of just like the computing, the horsepower that's on a laptop nowadays. You have to do it ends up being, as I said, like, there are 511 different ways of splitting up a given column. If you've got 10 columns, then that's 5,110 different splits that you have to go through to figure out the very first question ask. Now, 5,000 operations for your computer runs at gigahertz speed, so you're talking like billions of calculations per second. And so that means ultimately, you're doing this in microseconds. So it's actually crazy fast. So, a handful of microseconds needed to calculate that first level of the tree. And so by the time you're done, maybe a couple hundred microseconds for the entire process, modulo, I don't know, some computer science-y stuff that I'm not factoring in here. But the bottom line is the brute force approach just works because our computers have so much horsepower.
Nice. Thanks.
Cool. Yeah, no problem. So yeah, I mean, I hate to say this halfway through the office hour, but like pretty much now that you know how this tree is built. So essentially you're just going to rinse, lather, and repeat. So let's start from here. After we figured out that, okay, height is the best first question to ask because we've tried all the different possible columns and split points for each column, and we've calculated the weighted average mean squared error for each. We found the one that minimized that, and it was height less than or equal to 6.1 feet. Now we focus on the next bucket that we want to pay attention to, and let's say it's this guy here. So again, we're going to start from these 272 samples, and we'll try every column. Again, they're all 10 columns, by the way, are available once again. So even though we used height to do the split, we decided height was the best question to ask about, or the best feature to ask about. That doesn't mean that we can't ask about height again. The column is still there, right? It's just an open question as to whether that's yet again going to be the best thing to ask about once more. If you're having trouble kind of with the intuition around that, again, think back to the game of 20 questions. If the first question I ask you in the context of the game is like, is the person you're thinking about older or younger than 40 years old, right? And then let's say you say it's younger. Well, it's possible that the next best question for me to ask is about age again. Maybe it's helpful for me to know, okay, fine, are they older or younger than 20 years, right? So it's totally cool, totally legit to ask about the same feature repeatedly. And that's why you're actually going to see down this tree, right, so weight ends up being the feature you're asking about in this particular bucket. And then look at this, the next one down here. Again, we're asking about weight. So that's totally fine, totally acceptable. But anyway, so we're at this level of the tree, and we'll repeat the process. We'll go through, this time, all 272 samples. There's still 10 columns, and so we're going to end up asking like roughly 2,700-ish questions, and again, calculate the weighted average mean squared error for each one, and then pick the one that minimizes that. It ends up being, is the weight less than 182 pounds, and so on. So you just repeat that all the way down the tree, and the tree grows out. Okay? That's how you end up with a tree structure that in principle can go on for as long as you have samples. At a certain point, you'll end up with like all your samples used up, and you'll have one sample per bucket. And that tells you that you've gone a little too far, and we'll talk about that case in a minute. But first, I want to point out something, and that is that there are these terminal nodes at the very end. They're called leaf nodes, and that's the buckets that you end up with at the very end of the tree. Okay? So once a sample ends up at the very end in one of these buckets, what do you think our prediction is going to be for that sample? Like, let's say we have a hockey player who ends up in, I don't know, in this bucket here. What do you think our prediction is going to end up being? Any takers?
Is it just the mean?
Yeah, that's right. It's just the mean, right? Because the whole thing we've been doing, like this whole time, we've been putting excruciating effort into trying to make sure that the mean is a good representation for the true value of samples that fall in a particular bucket. Why do that unless we're going to use the mean as the predictor at the end of the day? And that's exactly what we're going to do. So suppose you have a hockey player who, I don't know, is like, what is that? Is taller than 6'1", so he ends up here. Let's say he weighs less than 196 pounds, so he ends up here. And let's say he's making less than $1.4 million a year, so he ends up here. Our prediction is going to be that he's going to score 15.1 goals in that season. Okay? So those leaf nodes, those final buckets, are you just have to look at the average value of the players who ended up there during the training process, and that's going to be your prediction at test time or at inference time more broadly. So that is kind of a quick overview of how these predictions are generated, but there's all kinds of really cool extra information that you get too. And not a lot of people realize this and not a lot of people use this, but you totally can and should after this office hour when you do your own projects and stuff. You'll notice in these final buckets, not only do we have a prediction, right? So we have a predicted value. Okay, a player in this bucket is going to score 31 goals at the end of the season. A player in this bucket will score 23 and so on. We also still have that juicy mean squared error. What does that mean squared error tell you? Well, remember, it tells you how bad this value is, this mean value, mean number of goals scored by, in this case, these 86 players who ended up in this bucket during training, as an estimate for the true number of goals that each individual player in this 86 group of 86 players will score. The bigger this MSE is, the worse this estimate is. In other words, this MSE is actually an estimate for how confident you should be in your tree's prediction about the number of goals that a player who ends up in this bucket will score. So this is like a really cool kind of bespoke aspect of these decision trees. You can make a prediction and you can say, okay, based on this player's characteristics, not only can I tell you what the number of goals that I expect this player to score is, I can also tell you how confident I am in my estimate. Because if the 86, in this case, players who ended up in this bucket during training had like still a really big spread, that means I wasn't really able to satisfactorily like pin down the true number of goals scored by the individual players in that data set. And so my MSE is going to be higher. You know, that's sort of what that means. So I don't know, I always thought this is kind of cool. Decision trees have this over, for example, logistic regression. You actually can get a reliable, customized estimate for uncertainty based on the characteristics of a given player. And this is something that, again, not a lot of people know, not a lot of people use, but it can make you seem like you really know what you're doing if you pull it out. Another thing to notice is you actually can see, based on this tree, like how many samples ended up in this bucket during training, right? So we have 96 players who ended up here, 86, 47, and so on, and it allows you to spot buckets where, like for example, this one here, only 15 players ended up here during training. So maybe unsurprisingly, we actually have a higher MSE in that bucket, and like it's up to you whether you choose to take that bucket particularly seriously. But it gives you at least a sense of how your training samples are distributed and whether there's a risk that you're going to make an error based on out of sample a player who comes in kind of like in an out of sample distribution. So anyway, that I think is maybe good motivation for paying close attention to these kinds of plots and diagrams. Another interesting feature of these decision trees, you'll notice that there's a finite number of leaf nodes. We've got 1, 2, 3, 4, 5, 6, 7, 8, unless my math is wrong. So 8 different final buckets, right, in this tree. Now, that actually means that this decision tree is mathematically incapable of predicting more than 8 different values. You put in a player into this decision tree, and it will never give you anything other than 31.1, 23.4, 18.1, 15.1, 16.7, 15.4, 13.2, or 8.1. Those are the only predictions this tree is even theoretically capable of spitting out. This is highly counterintuitive, especially in a regression context. This is unlike logistic regression, which can actually give you a continuous prediction output. And it's something worth keeping in mind. So typically, the reason these trees are so well behaved in the wild is that they tend to be deeper than just like, having eight leaf nodes, which I have here just for kind of illustrative purposes. Usually you have far more, so you get more resolution. But at the end of the day, you are constrained to just the number of leaf nodes that you've got. That's the number of different predictions that you're gonna give out. So anyway, just a little counterintuitive thing there. Any questions about this stuff so far?
It's interesting that like regression trees decision trees when you're doing regression are almost like classification tree. It's almost like you're using classification, but you're pretending to do regression. So that's kind of cool. And another thing about the uncertainty measurement, I've done a little bit of Bayesian statistics, and it's a lot easier to get an uncertainty measurement with one of the decision trees, and I kind of appreciate that a little bit more than the whole complicated prior posterior world in Bayesian statistics. So it's something that I really appreciate. I think about random forests and decision trees in general. So that's kind of really cool.
Yeah, good point. Actually, with the Bayesian comparison, one thing that's worth noting too is like you want to make sure that you're keeping in mind what this MSE means, right? So this does not mean like let's say a player ends up in this bucket. Prediction is 18.1 goals. It's not 18.1 plus or minus 2.49 because if you look at the formula for the mean squared error, it's not quite. It's not in the same units as the thing you're trying to predict. We can get into that in more detail, but the bottom line is this is more just kind of a number that gives you a relative sense of the uncertainties. And again, we can dive into this if there are questions specifically about that. But yeah, it's a very, you can think of it as like a hacky kind of engineering type way of just getting a guesstimate of what that uncertainty would be, and much easier to understand and compute than the full rigorous Bayesian approach, which can sometimes be intractable. Sorry, did somebody just unmute?
Just another quick
Chris.
question. So do decision trees always use the statistical mean as their predictor, or are there like other weird variations that can use like a different predictor function?
Yeah, great question. So for just about all practical purposes, when you're doing regression, you will be using the mean. That's what scikit-learn's default is. You can enter custom functions, and if you're ever doing that, you'll be putting a lot more thought into exactly what it is that you want to optimize for. But in general, like I would say 95% of the time, it ends up just being the mean for regression.
Okay, thanks.
Yeah, no problem. And actually, to Nicola's point, so you actually do see with classification problems, almost exactly the same process unfolds, right? Like you end up with these final buckets. In a way, it just kind of seems more intuitive because with a classification problem, you sort of expect to have a finite number of buckets at the end of the day. Like maybe you're predicting who somebody's going to vote for or whatever, who's going to be team captain on the hockey team or something like that, and you have like captain and not captain, right? So it kind of makes sense that you're going to have a finite number of buckets. What I think is kind of counterintuitive about these regression trees is, number one, that they still have a finite number of buckets, even though they're predicting a continuous variable, and number two, that they actually work so well, despite that. So this is something to, I guess, keep in mind, and part of the reason why I actually wanted to show you guys a regression tree as the example. I didn't want to run with the classification version just because everyone always assumes that's what decision trees are good for. I want to show you there's actually a bigger universe here. The hardest conceptual version of this decision tree to grapple with is the one you're seeing here. It's the regression version. Cool. Oh yeah.
Another quick question about having an outlier in our training data set. So I was thinking, if you have an outlier, the algorithm is going to be prone to split it on top levels and just put the outliers on one bucket and then continues on? Or how is it going to react to outliers, generally speaking?
Yeah, good question. So we can actually flip back and kind of imagine a concrete outlier. So usually the way an outlier is just going to end up making your final buckets a little bit worse, right? So outliers are points that don't behave like other points. So as you're going through it, you just kind of got this annoying little extra sample that almost like gets randomly assigned to different buckets as it flows all the way through. And that's part of the noise that you'll get at the end of the day. So you definitely want to remove outliers first when you're working on your decision tree. If the proportion of outliers is small enough and their deviations are small enough, then they don't tend to cause that much of a problem. But you can definitely, like, one giveaway is if you have a bucket that seems to have a reasonably high number of samples at the end of the day, and yet its MSE is like suspiciously high, that might be an indication that you have an outlier in that bucket. It might tell you like, okay, there's one of these samples that the algorithm just couldn't shake off, and yet it doesn't really seem to belong in this group. So that's something to look at for sure.
So does it make the decision tree like a kind of robust algorithm like towards outliers compared to other basic algorithms like logistic regression?
I don't think it's particularly. I don't think it's actually. Sorry, I need to think about this a little bit more. I want to say it probably is slightly more so than logistic regression because you might get lucky and isolate the outlier in like its own leaf node. At the end of the day, you might have an n=1 leaf node or something like that. But there's no obvious reason off the top of my head that it would be more or less robust by a significant amount.
Okay, thank you.
Yeah, no problem. Good question. I mean, I'm sure there's an answer out there somewhere. No problem. Justin, did you unmute yourself? Or?
Yeah, so in scikit-learn or whatever you use to generate these, does it give you those bottom leaf nodes, like the composition of those? Can you pull those and kind of inspect their distributions as a way to sort of check the quality of your decision tree?
Yeah, good question. So I know you can certainly generate this this plot. I'm not sure about methods to inspect the like kind of meta statistics of the leaf nodes. That'd be worth looking into. You certainly can actually you certainly can navigate through the and manipulate the graph itself. So actually, the answer is going to be yes. It's just a question of like I don't think there's a single function that you can use to be like yeah. But yeah, you can definitely kind of dance through the graph in scikit-learn and look at individual nodes.
I don't know if we mentioned, maybe we did, so pardon for repeating, but one thing I think it's cool to note, important to note about decision trees is they usually overfit a lot. So
yes,
as great Andrea Capati said, always overfit first, which is a good thing. But they do always overfit. So you in production probably. Like I never really use decision trees in production. I like from so far, so what I've seen, random forests are more common, or any other ensemble, XGBoost, whatever.
Okay.
But yeah.
So actually, this is like I could not have asked for a better segue. So thank you, Nicola. So I want to get into exactly that question. So yes, decision trees do or can overfit. I will add the caveat, they actually can be good in production as well. You're right. I mean, random forests almost always are better, but let's just flip back and ask the question. This is related to something Chris said earlier too. Like, what is it about decision trees that makes them so prone to overfitting? Well, if you don't rein in a decision tree and you just let it ask question after question after question after question, eventually you'll end up with a single sample in each leaf node. So in our example, you'd be splitting, you'd say like, is the hockey player shorter than like 6 feet? Like by the time you get all the way to the bottom, it might be like, is the hockey player between like 6 feet and 6'1", and is their weight between 180 and 181 pounds? And like, are they getting paid between like $2.1 million and $2.4 million a year? So you have this little like kind of conspiracy fit around this individual point because you've asked so many questions that you've narrowed things down to the point where there's 1 point per bucket. That is the definition of overfitting. Overfitting is a little conspiracy that you make around each individual data point, and that's a problem. So essentially, what you have to do is, there's a reason, by the way, that the game of 20 questions is the game of 20 questions, and it's not the game of infinity questions, because the game of infinity questions would be pure overfitting. And the way you would play that is you would say something like, is the first letter of the name of the person you're thinking of A? No. Okay. Is it B? No. Okay. And you would keep going, and you would eventually, you're not actually demonstrating generalizable knowledge, you're just overfitting completely to your data set. So the same thing can happen with decision trees if you just let it go indefinitely, which means we've got to stop that process somehow. We have to impose restrictions on the tree's ability to go as deep as it wants to go, because otherwise it absolutely will overfit. So how do we do that? Well, a whole bunch of different options. First one is the kind of the dictator's approach, where you say, okay, that's it. You're not allowed to ask more questions than this. And that's called the max tree depth parameter if you look at scikit-learn, or sorry, max depth parameter. You can specify, it's a hyperparameter that you can specify in your training algorithm that says, okay, max depth is, let's say, 4, and that means you're not allowed to ask more than 4 successive questions. And that's actually possibly the value actually that's being set here. If you look at, there's one question here, another level of questions here, and a third one here, and then a fourth one here. So that's, plausibly max depth of 4 would have been the hyperparameter value here. But that's not the only way. You could also say, I want to say there's a maximum number of leaf nodes. So for example, in this case, max leaf nodes might be set to 8, right? So we've capped off the maximum number of final nodes. And that again is also basically aimed at the same thing. You're trying to make sure that you can't keep proliferating those leaf nodes until you have 1 sample per node. Another strategy you can use is, or another hyperparameter, is called min samples split. And this is the minimum number of samples that you'll need in a bucket in order to justify splitting that bucket. So in this case, we have, I guess the lowest number of samples in this tree is 15, right? During training, this bucket here got 15 samples. So maybe min sample split is set to something less than 15, and that's what stopped this bucket from continuing, right? So those 3 variables are the most important ones. If you look at the scikit-learn decision tree API, you'll see all 3 of them. You'll see max leaf nodes, min sample split, and max depth. And you can make a grid search to optimize your way through all those hyperparameter values. And once you do that, you'll end up with some Frankenstein monster of a tree like this that kind of seems like it randomly stops, like in this case at level 2. Other samples end at level 3, and others make it all the way to level 4. So that's all kind of factored into this particular tree here. But the bottom line is you're trying to avoid that overfitting problem that presents itself otherwise if you just let the tree go ham and go as far as it wants. Any questions about that?
How about pruning as a means to avoid overfitting? So removing the nodes that are too complex. I'm sorry, that might be too complex or might be too resource expensive for the model to run.
Yeah, so typically pruning is something that you'll see a little bit more in like tree ensemble models, like individual decision trees. It doesn't tend to come up quite so much just because they're so well defined in terms of the process that's used to build them up. Yeah, I mean those 3 hyperparameter values are the ones that typically go into tuning these things. Pruning is something, yeah, you will tend to look at more with like XGBoost, random forest, and that sort of thing.
I had another follow-up question.
Well, yeah, go ahead.
Yeah, because I noticed that your example doesn't use any categorical data, and is there any conventional wisdom or even a hard rule about using exclusively, for example, categorical data in a decision tree model?
Yeah, great question. Now you're making me wish that I had included a categorical variable. I really should have. Okay, so the good news is that the categorical variables, if you think about it, they actually can get treated the exact same way as the other variables. So let's invent a new one for hockey. Yeah. So hockey players have, like in soccer, I think in soccer you have like attackers and defense. I don't know. In hockey you have forwards, defensemen, and goalies. So let's focus on forwards and defensemen because they're actually trying to score goals, which is the thing we're trying to predict. So a forward is probably going to score more often, and a defenseman is probably going to score less often because they tend to sort of fall back. That's a useful categorical variable. So let's imagine we're at the very top of our process here, right? At the very first step, we have all 512 samples. We're trying to decide which question to ask first. And we're going through all of these 10 different columns, and now let's imagine we're adding an 11th that says, are you a forward or a defenseman? And well, in this case, we would just have one split to test out in that sample. We'd try the obvious, are you a forward or a defenseman? And you'd get a weighted average mean squared error for that split. Maybe one bucket, the number of goals you'd expect for the forwards bucket to be much higher than the number of goals scored for the defenseman bucket. And hey, maybe that's actually the best question to ask. And if that's the case, then that will get locked in, and you would proceed with the analysis in a similar way. Does that make sense?
Yeah, thank you.
Hadrian, looks like you're still. Okay, great. Yeah, no problem. So yeah, again, this is one of the other reasons I love decision trees is they're so freaking robust, right? Like you throw in categorical data and they don't even flinch. In fact, they even perform better. They're really designed to handle that kind of data very well. I think one of the surprising things, almost miraculous things, is how well they deal with non-categorical data, things like height, weight, and so on, as we've seen here today. So yeah, kind of a cool thing. One quick note that I'll toss in before we wrap things up, individual decision trees, actually, as Nicola said, still can overfit. So you can still play this game of saying like, okay, I want to optimize my hyperparameter values, my max tree depth, min sample split, all that stuff, and you'll still overfit somewhat with these decision trees. And so the solution to that is usually to put a whole bunch of different decision trees together in an ensemble, in a group of decision trees, and then you let each one of them make predictions independently and then take the average. At least if you're doing a regression problem like this one, you would take the average. So say we've got 10 different decision trees. The first one says, I predict this player is going to score 10 goals. The next one says 8. Then you average those two out, and the prediction of that ensemble of 2 trees would be 9 goals. Okay, so that's sort of how you start to build these forests of trees, hence random forests. There's a little bit more nuance to it that we don't quite have time to get to, but that's at least the spirit of that philosophy. Any other questions about this stuff? Okay. All right, well, I'll close off with a bit of good news, which is now that you understand decision trees very deeply, one thing you'll very quickly notice is like most of the models in the particle zoo, I think arguably, of the machine learning zoo, arguably are tree-based. So, random forests, adaboost, XGBoost, gradient boosted machines, pure decision trees, these are all tree-based models. And like once you finish looking at them, like, there aren't that many models besides those. There's like logistic regression, support vector machines. There's like naive Bayes, KNN, pretty much it, right? Like there's not that much else. There's maybe like 4 or 5 other models. The vast majority of the richest, most cutting edge models, actually, things like XGBoost that have won Kaggle competitions historically, are tree-based. And there's a very good reason. They're very interpretable. They give you free uncertainty estimates at the end of the day from these buckets. You can interrogate them. You can do a lot of cool things with them that other models don't allow you to do. And so they're really worth understanding quite deeply. And anyway, that's a topic for a future occasion. We will look at ensemble models. You can see actually previous office hours where we have talked about those, and we'll be talking about those again in the future as well. So maybe this is a good place to stop. But if anybody has any questions, feel free to ask away now. If not, we'll reconvene on Slack. All right. Cool. Well, have yourselves a lovely Monday evening, everybody, and we'll see you guys next week.